Complete virtual memory systems. We've seen key elements of such systems, including numerous page table designs, interactions with the TLB, sometimes even handled by the OS itself, and strategies for designing which pages to keep in memory and which to kick out. However, there are many other features that comprise a complete virtual memory system, including numerous features for performance, functionality, and security. So we discuss all the basics, the page table designs, interaction with TLBs, even handled by the OS itself. Now we will discuss how it works completely or all throughout the system, including performance, functionality, and security. The crux: how to build a complete VM system, what features are needed to realize a complete virtual memory system, how do they improve performance, increase security, or otherwise improve the system. So what features in this system or in this live virtual memory system, how do they improve performance, security, and otherwise improve the system? So let's look at the history. We'll start with VAX or VMS virtual system. We discussed this in the previous video, but yeah, the VAX 11 mini computer architecture was introduced in the late 1970s. So basically, it was the first virtual memory that we will discuss. As an additional issue, VMS is an excellent example of software innovations used to hide some of the inherent flaws of the architecture. Although the OS often relies on the hardware to build efficient abstractions and illusions, sometimes the hardware designers don't quite get everything right. In the VAX hardware, we'll see a few examples of this and what the VMS operating system does to build an effective working system despite these hardware flaws. So, how do you build on top of that hardware flaws? So, VAX actually, system engineers of VAX named Dave Cutler already solved this for us. First, memory management hardware. The VAX 11 provide a 32-bit virtual address space per process. So it started with 32-bit divided into 512-byte pages. Thus, a virtual address consisted of a 23-bit VPN and a 9-bit offset. Further, the upper 2 bits of the VPN were used to differentiate which segment the page resided within. The system was a hybrid of paging and segmentation. So this system used the concept we discussed earlier, however, the hybrid of that. Remember that whenever we have some good features of two different, seemingly completely different system, we may think of using both. So here is the application of that. And the first 2 bits or upper 2 bits of the VPN actually used to differentiate the which segment the page resided. The lower half of the address space was known as process space and is unique to each process. The lower half of the address space is called the process space and unique to each process. So the lower half of this address space provided to the process are unique to each process, and the first 2 bits are actually to differentiate the segmentation for that. So again, the different segment could be code, heap, and stock. In the first half of process space, known as P0, the user program is found, as well as a heap which grows downward. Again, in the first half of process space known as P0, the user program is found. So again, the last space are the unique virtual address for that process. However, in the first half of process address space known as P0, which is this, the user program is found. So this is where the user program, the user code, heap, and page 0 is invalid. Notice we don't have the stock that yet on that 0. As well as heap which grows downward. Sorry, in P0, or the first half, actually include the heap, the user heap here, but the stock it's in P1. In the second half of the process space P1, we find the stock which grows upwards. So these are the second half of process space. Again, it's the second half of the process space. We have the stock which grows downward. The upper half of the address space is known as system space, S. So these are the upper half of the address space. So again, the upper half of the address space is known as system space, which is this. The lower half of the address space is known as the process space. As you can see, that's P1 and then P0. So think of this as the upper, kind of like the opposite, although only half of it is used. So here, the system space, only half of it is used. Protected OS code and data reside here. So the use space are the protected code and data, which we're gonna discuss later. And the OS is in this way shared across processes. So in this way, the VAX virtualized the OS and shared the this kernel code and data across processes, but it still starts at the frame 0 on the physical memory. It just virtualized this. So it's the same concept we discussed before. I mean, any space or any frame physical address in memory would be fine, but it still have that kernel or OS code and data at the start, or will boot first before any program. So this is the virtualization of that. As you can see, we also have unused space. One major concern of the VMS designers was the incredibly small size of pages in the VAX hardware, 512 bytes. The size chosen for historical reasons has the fundamental problem of making simple linear page tables excessively large. So one of the uh, hardware problem that we want to solve via OS is the size. So the size chosen for historical reasons is excessively large. So again, previously we discussed sizes of pages such as 4 bytes. Now we're seeing 512 bytes. Thus, one of the first goals of the VMS designers was to ensure that VMS would not overwhelm memory with page tables. So one of the goal is not to overwhelm it with page tables. And remember, page tables leads to large page sizes, or a lot of page table could lead to external and internal fragmentation. Now, to solve that first, by segmenting the user address space into two, the VAX11 provides a page table for each of these regions, P0 and P1 per process. So, first solution is to segment it per process, or the user address space into two. Provides a page table for each of this region, P0 and P1. So it divides the user address space into two, which P0 and P1. Thus, no page table space is needed for the unused portion of the address space between the stock and the heap. So by doing that, as you can see, we have user P1, user P0. By dividing that into two, there's no page table required to allocate or track this unused table between the stack and the heap for the for both for the process, because we divided by two. As you can see, guys, this is just one process. User code, this is the user heap and the user stock, but we divide that into two user space. The base and bound registers are used as you would expect. So this is the application of the base and bound register in real life virtual memory. A base register holds the address of the page table for that segment. So again, to go back to the basic, the base register hold the address of the page table for that segment. So let's say you have this segment P0, the base register for that hold that address for that, and the bounds holds its size, like the number of page table entries. So again, the size of the page table depends by the number of page table entry. And remember, the page table entry has that protection modified bits. So the feather, depending on the number of configuration on the page table entry, that will determine the size of that page table entry, and depending on the number of the pages on that page table will depend how many page table entries you have, because page table entries will dictate the number of pages you have in page tables. Second solution, the OS reduces the memory pressure even further by placing user page tables for P0 and P1, thus 2 per process. in kernel virtual memory. Again, second, the OS reduces the memory pressure even further by placing user page tables in a kernel virtual memory. So we divide that into two. That's one of the solution. Additionally, we place that their page table of these two address space in kernel virtual memory, or again in this system space. Again, that's a virtual memory. That's just a virtual memory. Thus, when allocating or growing a page table, the kernel allocates space out of its own virtual memory. This the unused. In segment S, if memory comes under severe pressure, the kernel can swap pages out of this page table out the disk. Thus making physical memory available for other users. So under pressure, it transfer first this space to disk, and the user could swap in from disk to its memory. Putting page tables in kernel virtual memory means the address translation is even further complicated. So there is an advantage on putting the page table there, because then in kernel virtual memory for those two user address space, but because you can swap out spaces from, you can borrow space from kernel, but at the same time there is a cost in address translation, which could further complicate this. For example, to translate a virtual address P0 or P1, the hardware had to first look up the page table entry for that page in its page table, the P0 or P1 page table for that process. In doing so, however, the hardware may first have to consult the system page table, which lives in physical memory. So in doing so, since you have this process saved in the system page table, to be able to check that page table of your process, whether it's P0 or P1, you need to consult the kernel physical table or frame table, page table, and then its virtual page table. With that translation complete, the hardware can learn the address of the page table. So after that, then only can the hardware learn the address of the page table. So again, it's trying to find the address of that P0 of the page table of P0 or P1. Then finally, learn the address of the desired memory access. So after it finds its page table, it then only gets the actual memory address. So all of this fortunately is made faster by the VAX hardware managed TLBs, which usually hopefully circumvent this laborious lookup. So there is a cost. We on top of that OS, we place the page table. So using the software, we use a page table on the kernel to track the page table of 0 and 1. But later on, we also use the hardware, using its hardware managed TLB, which we discussed in the previous video, to help that OS. So it's kind of like making the use of OS first and then the hardware managed TLB to be able to make it efficient. Aside the curse of generality, operating systems often have a problem known as the curse of generality, where they are tasked with general support for a broad class of application and systems. The fundamental result of the curse is that the OS is not likely to support any one installation very well. In the case of VMS, the curse was very real, as the VAX 11 architecture was realized in a number of different implementations. It's no less real today, where Linux is expected to run well on your phone, a TV set-top box, a laptop computer, desktop computer, and a high-end server running thousands of processes in a cloud-based data center. So before even today, there's such thing as a curse of generality, where the more you generalize, kind of like in about phase, the more you not serve the people you were designing or trying to help in the first place. So there is a cost, time and cost trade-offs with generalizing. A real address space. So this is an example of the VAX, or the real address space, in practice. Thus far, we have assumed a simple address space of just user code, user data, and user heap. But as we can see above, a real address space is notably more complex. So we have a page table tracking those page 0 divided page 0 and page 1, and we have a hardware managed TLP. That's what makes it notably more complex. For example, the code segment never begins at page 0. This page instead is marked inaccessible in order to provide some support for detecting null pointer accesses. So the code segment never begins at 0, just like we discussed in the previous video. It doesn't actually work like that in the real world, as you can see here. So it marks usually invalid in order to provide support for detecting null pointer accesses. So to detect a null pointer access, because again, a null pointer access will return a null. So this is the part of the space of the process that we use to return that null. Thus, one concern when deciding an address space is support for debugging, which is inaccessible zero page provide here in some form. So the use of this is usually for debugging. That's the reason why it's usually you don't have a code at the beginning of the space. Perhaps more importantly, the kernel virtual address space, its data structures and code is part of each user address space. So another thing, since we have the page table of each P0 and P1, each process address or user address space actually have the kernel virtual address space, its data structure and code. So it can vary, some information whenever it wants to drop into the OS, because it makes the transfer of commands easier, like kind of like the drop into the OS. So on a context switch, the OS changes the P0 and P1 registers to point to the appropriate page tables of the soon-to-be-run process. So this P0 and P1 is just actually one process. Now, if we, for example, allocate another process or context switch to another process, the P0 and P1 registers to point to the appropriate page tables of the soon-to-be-run process. So it changed the register. So the reason it changed the register, because again the register are used to measure the size. So therefore, once we allocate something, as long as it is enough, we have enough memory, we will allocate some memory for it. Therefore, we will lessen the size for the previous context, and we don't use that context or process anyway. And the scheduling algorithm will run to run that later. However, it does not change the S base and bound registers. So what it does not do is it does not change the S or the system base and bound registers, so it stays the same. So you cannot change that because that's the kernel code. Kind of like it's protected, the code of that kernel, because those don't change. And as a result, the same kernel structures are mapped into each user address space. That's also one of the properties that allow us to map it to each user address space as we allocate a base and bound register to it, or a space for it. The kernel is mapped into each address space for a number of reasons. So this construction makes life easier to for the kernel when, for example, the OS is handed a pointer from a user program, like on a write system call. It is easy to copy data from that pointer to its own structures. So aside from you know tracking it to make the OS and hardware work, another advantage of having the kernel map its data and the code to each process address space is that when a program call write system call, it's easy to copy data from that pointer. Let's say that pointer is from the stack, and then we'll be writing to physical memory, because the OS is naturally written and compiled without worry of where the data is accessing comes from. So without worrying about the address translation, or where the data or process the data came from, where is the address of that process calling from. If in contrast the kernel were located entirely in physical memory, it would be quite hard to do things like swap pages of the page table to disk. So if we don't have this virtual memory, it will be hard to swap pages of the page table to the disk. For example, since this kernel have in actuality a page table or a copy of a page table for this process address space, and because of that, it can easily allocate its unused space to the disk, and then later provide to the process. And also remember, the OS has a direct access onto the file system or the disk, unlike the processes. If the kernel were given its own address space, moving data between user applications and the kernel would again be complicated and painful. So if we provided a separate address space without being connected to the user code and data, it will be hard to just write that simple system call to the disk and conduct that I/O, and it will be complicated and painful. So that's how it is complicated in the real world. With this construction, now used widely, the kernel appears almost as a library to applications, albeit a protected one. is again, it can use the dirty bit, the protection bits, etc. But it's still in the virtual address space instead of the physical address space. As you can see, guys, it's abstracted to make it to make it appear a virtual or an illusion that you are using the actual application. One last point about the address space relates to protection. Clearly, the OS does not want user applications reading or writing OS data or code. So since the OS data or code is shared, as long as that is allowed operation, but at the same time, the OS does not want the program to write. So that code should be read only. No, to write that OS data or code in that kernel virtual memory. Thus, the hardware must support different protection levels for pages to enable this. So again, the hardware saves us on this again. So as you can see, the mechanism and the policy working together to be able to create this solution. The VOX did so by specifying in protection bits in the page table what privilege level the CPU must be at in order to access a particular page. So the page table that we have in kernel that has the page table of the P0 and P1, which then later connect to the actual physical memory, has the actual configuration, or the VOX actually has a configuration of that in protection bit in that page table to determine the privilege level it can do on the CPU at a particular page or page of that process. Thus, system data and code are set to a higher level of protection than user data and code, and an attempted access to such information from user code will generate a trap into the OS. And you guessed it, the likely termination of the offending process. So again, the system data and code are set to a higher level of protection than user data and code. An attempted access to such information from user code. So if a user code attempted to access kernel data and code, it will likely terminate that user process. Page replacement. The page table entry in VOX contains the following bits: a valid bit, a protection field, 4 bits, a modify or dirty bit. So this is the page table entry that also determine how large is our page table that we convert to physical frame in VOX. Again, we have a valid bit, protection bit, 4 bits. So this the one that determines the privilege level is actually just 4 bits, which is the protection bits. Modify or dirty bit, a field reserved for OS use, 5 bits. So as you can see in this page table entry, on the actual page table physical frame, we have 5 bits reserved for OS. So these are the bits used in each in sharing the code and data for each processes. And finally, a physical frame number to store the location of the page in the physical memory. The astute reader might note no reference bit. Thus, the VMS replacement algorithm must make do without hardware support for determining which page are active. The developers were also concerned about memory hogs. So this VOX again doesn't have the reference bit. Therefore, the VMS replacement algorithm will make do for what it has. So as we have learned, an OS could be used to track the recently accessed bits to determine if it's a modified or dirty bit. The developers were also concerned about memory hogs, the programs that use a lot of memory and make it hard for other programs to run. So again, the developers were also concerned about memory hogs. programs that use a lot of memory and make it hard for other programs to run. So these are the uh, things that we encountered in the previous video as well, where some the threads uh, kill the largest process for Linux, while the other form of VM policy or other VM policy just removes some of the tasks to make free to the memory. So most of the policies we have looked at thus far are susceptible to such hacking. For example, LRU is a global policy that doesn't share memory fairly among processes. So LRU, though it may be good for prioritizing, is doesn't actually share memory fairly, because again it's kind of more like a priority based policy than a proportional based, like what we discussed in the scheduling policy. So most of the policies we have looked at thus far are susceptible to such hacking. To address this problem, the developer came up with the segmented FIFO replacement policy. So to address that memory hacking, aside from that clock replacement policy, there is segmented FIFO replacement policy, which is actually applied in the real world, which is BACS. The idea is simple. Each process has maximum number of pages it can keep in memory, known as its resident set size. So it doesn't get more than it is allocated to. Each of these pages is kept on a FIFO list. When a process exceeds its RSS, the first in page is evicted. So that's the reason why it's FIFO replacement, segmented FIFO replacement fallacy, because the first pages that comes to that page or to that process will be evicted if it exists its RSS. FIFO clearly does not need any support from the hardware and is thus easy to implement. So it's another way of using policy to help the hardware limitation. Of course, pure FIFO does not perform particularly well, as we saw earlier. To improve FIFO's performance, VMS introduced 2-second chance list where pages are placed before getting evicted from memory. Specifically, a global clean page free list and a dirty page list. So to improve that, again, just like how we improved the LRU and clock algorithm before, we added a list to track the modified and unmodified bit. When a process P exceeds its RSS, a page is removed from its per process FIFO. If clean, not modified, it is placed on the end of the clean page list. If dirty, modified, it is placed on the end of the dirty page list. If another process queue needs a large page, it takes the first free page of the global clean list, because again it doesn't have that writing to the disk, therefore we can freely clean it, or we can freely reuse that page. However, if the original process P falls on the page before it is reclaimed, P reclaims it from the free or dirty list. Thus avoiding costly disk access. So if that original process then revert to changes and not write anything to the disk, it reclaims it from that dirty list. So it removes the system, or this improvement removes that from the dirty list, so that we avoid the cost of writing it again. So a lot of things that we remove on our PC or in our computer are actually being done in memory. A lot of times they don't do the IO first or saving that actual memory. They cluster that, as we have learned in the previous video. Now this is the application of that. But in this case, it just track it if it's reverted in a original version, and avoid saving it altogether. The bigger these pages, the bigger this global second chance list are, the closer segmented FIFO algorithm to perform to LRU. So remember how LRU perform approaching optimal replacement policy. Now the bigger this second chance list, or the bigger we allocate space for this, the closer it is to perform with LRU replacement algorithm, therefore achieving the optimal replacement policy. Another optimization used in VMS also helps overcome the small page size in VMS. Specifically, with such small pages, disk I/O during swapping could be highly inefficient. So since VMS has a small page size, there's another OS optimization. Specifically with such small pages, disk I/O during swapping could be highly inefficient, as disk do better with large transfers. So these are the another optimization, as like what I've said, clustering those writes makes it efficient. So another way of using policy to make this hardware limitation work better. To make swapping I/O more efficient, VMS adds a number of optimization, but most important is clustering. With clustering, VMS groups large batches of pages together from the global dirty list and writes them to disk. So again, it optimizes, aside from this optimization of clustering, it builds on top of the optimization we've done with the segmented FIFO replacement policy, which is the dirty list. So we use that dirty list, globally dirty list, and writes them to disk in one fell swoop, thus making them clean. Clustering is used in most modern systems as the freedom to place pages anywhere within swap space lets the OS group pages. So because the OS has a freedom to place the pages anywhere, even it's non-contiguous in swap space, lets the OS do this: group the pages to write, perform fewer and bigger writes, and thus improve performance. Aside emulating reference bits, as it turns out, you don't need a hardware reference bit in order to get some notion of which pages are in use in a system. In fact, in the early 1980s, Babak, Lu, and Joy showed that protection bits on the VAX can be used to emulate reference bits. So we can actually, if since our VMS does not have the reference bit, it can actually use the protection bit. So this is another way software used to track those actively or dirty modified page. So the basic idea, if you want to gain some understanding of which pages are actively being used in a system, so aside from dirty or reference bit, that dirty is actually actively used to track to what process or pages are actively being used in a system. So if you want to gain some understanding of which pages are actively being used in a system, mark all of the pages in the page table as inaccessible, but keep around the information as to which pages are really accessible by the process. Perhaps in the reserve OS field portion of the page table entry. So since we have that reserve OS field in the page table entry, we can capitalize on that as well, aside from the protection bit. So we will mark all the pages inaccessible. So if that pages are really accessible, we put that in the reserve OS field. In the PTE, when a process accesses a page, it will generate a trap into the OS. The OS will then check if the page really should be accessible, and if so, revert the page to its normal protections, like read only or read write. So it will trap into the OS, and then the OS, based on that reserve OS field, will then check if what really is that code can access to, whether it's read or write. At the time of replacement, the OS can check which pages remain marked inaccessible and thus get an idea of which pages have not been recently used. The key to this emulation of reference bit is reducing overhead while still obtaining a good idea of page usage. So it reduces the overhead while at the same time you get an idea of what is the actual actively using page that is using. So the OS must not be too aggressive in marking pages inaccessible, or otherwise would be too high, or overhead would be too high. The OS also must not be too passive in such marking, or all pages will end up reference. Again, the OS must also not be too passive in such marking, or all pages will end up reference. The OS will again have no good idea which page to evict. So the entire reason to learn this is to know what page to evict by the OS. So this emulation reduces the overhead from the memory while still having good idea what is being referenced to most often by the processes, what pages. Other neat tricks, VMS had two other now standard tricks: demand zeroing and copy on write. So this is another like software that capitalize optimization of software that allows you to do more with limited hardware. We now describe these lazy optimizations. One form of laziness in VMS and most modern systems is demand zeroing of pages. To understand this better, let's consider the example of adding a page to your address space, say in your heap. In a Neve implementation, the OS responds to a request to add a page to your heap by finding a page in physical memory, zeroing it required for security. Otherwise, you'd be able to see what was on the page from when some other process used it. So for normal implementation, you would find that in the memory, zero it, and then provide that or allocate that to the heap, and then mapping it into your user address space, like the heap, setting the page table to track it, to refer to that physical page as desired. So again, that page table track the processes from virtual memory. It is not in physical memory because of the translation overhead needed for disk transfer, and then swapping of space from disk to memory. So that's the Neve implementation. But the Neve implementation can be costly, particularly if the page does not get used by the process. But the Neve implementation can be costly, particularly if the page does not get used by the process. So let's say that process allocate that using malloc and you zero it. So this could be costly if it doesn't end up using it, even if it allocated it. With demand zeroing, the OS instead does very little work when the page is added to your address space. It puts an entry in the page table that marks the page inaccessible. If the process then reads or writes the page, a trap into the OS takes place. So only then if the process reads or write or actually does something after it allocate will it drop into the OS, kind of like the emulation of the reference bit. Or it's actually like that. When handling the drop, the OS notices, usually through some bits marked in the reserved for OS portion of the page table entry, that this is actually a demand zero page. At this point, so it uses again from this software we create, it capitalizes again the reserved for OS like the emulation of the reference bit. So it noticed that this actually the demand zero page. So we actually need to zero that page to be able to use because the process are actually using that page. At this point, the OS does the needed work of finding a physical page, zeroing it, and mapping it into the process address space. And that at that point, the OS actually does the required work of zeroing it, finding it in the physical memory using the PTE, updating the page table, and then having the page table of the kernel virtual memory track that space. So that's the demand zeroing. If the process never accesses the page, all such work is avoided. So kind of like in the emulation. And thus the virtual virtue of demand zeroing. So if the user program never end up reading or writing it, it is never dropped to the OS, and therefore all that process never access any page on the actual memory. Another optimization found in VMS and again in virtually every modern OS is copy on write, COW for short. This idea, which goes least back to the 10x operating system, is simple. When the OS needs to copy a page from one address space to another, instead of copying it, it can map it into the target address space and mark it read only in both address space. So instead of copying it to a target address space, it can map it into the address space and mark it read only in both address space. If both address spaces only read the page, no further action is taken, and thus the OS has realized a fast copy without actually moving any data. So this is the case where you have two processes like accessing the same physical frame or accessing the same virtual memory, because it is copy only. If however one of the address space does indeed try to write to the page, it will trap into the OS again. So this trap into the OS is so useful. The concept we learned in the previous video are where this applied in the real world. So it trap into the OS, it used the policy and the hardware. So the OS will then notice that page is a cow page and thus lazily allocate a new page. So it will notice that that is a cow page, therefore it will allocate a new page. So it's a cow page because it allows for reading only for fast copy, while at the same time if it's writing it, the OS drop into it and then the OS actually allocate a new page, fill it with data and map this new page into the address space of the faulting process. So after it tracks that in the page table, update the page table entry, it will now map that to the user address or faulting process. The process then continues and now has its own private copy of the page. So the process then continues and now has its own private copy of the page. So since it's trapped into the OS provide an allocated page, and now the process continues because it already have its actual page written too. Certainly, any sort of shared library can be mapped copy on write into the address space of many processes. So any shared library, because this first type of or VMS is actually a shared library, since the kernel is in virtual memory and all processes its data and code, kernel data and code. Therefore, we can map copy on write on this. So this is the what makes this OS or policy capitalize on this low memory or just 32 bits, saving valuable memory space. In Unix, cow is even more critical due to the semantics of fork. Remember the fork and exec. As you might recall, fork creates an exact copy of the address space of the caller with a large address space, making such a copy slow and data intensive. So since we use fork first to do the exec, so if we always do that, and we end up not doing that, that translation alone for large address space is low and a data intensive. So therefore, we use just the copy on this copy on write. So operating system use copy on write for those kind of operation. Even worse, most of the address space is immediately overwritten by a subsequent call to exec, which overlaps the calling process address space or overwritten that current process address space. So what does good what good it does if it will be overwritten to after that. So it's better to do a copy and write, which by a subsequent call to exec with which overlays the calling process address space with that of the soon to be exec program. By instead performing copy on write fork, so that's actually copy and write. We only write or allocate page if it's actually a write operation. The OS avoid much of the needless copying and thus retains the correct semantics while improving performance. Tip: be lazy. Be lazy can be a virtue in both life as well as in operating systems. Laziness can put off work until later, kind of like the clustering, which is beneficial within an OS for a number of reasons. First, putting off work might reduce the latency of current operation, thus improving responsiveness. Cow also has these attributes of putting off later, putting off the write, unless it is actually a write operation. For example, operating system often report that writes to a file succeeded immediately and only write them to disk later in the background. So that's actually what a modern operating system does. Like what I've said earlier, it provides you a confirmation that it is saved, but it only does that later in the background. Second, and more importantly, laziness sometimes obviates the need to do work at all. For example, delaying a write until the file is deleted. So when you actually revert that reversion, removes the need to do the write at all. Laziness is also good in life. For example, by putting off your OS project, you may find that the project specification bugs are worked out by your fellow classmates. Thus, you don't need to do the effort to fix that. However, the class project is unlikely to get cancelled. So being too lazy may be problematic if you go over it, leading to a late project, bad grade, and a sad professor. Don't make professors sad. So the Linux Virtual Memory System. We'll now discuss some of the more interesting aspects of the Linux VM system. Linux development has been driven forward by real engineers solving real problems encountered in production, and thus a large number of features have slowly been incorporated into what is now fully functional feature-filled virtual memory system. For this discussion, we'll focus on Linux for Intel x86. While Linux can and does run on many different processor architecture, Linux on x86 is most dominant and important deployment, and thus the focus of our attention. So though this operating system could run in many processor architecture, this application x86 is its most dominant and important deployment. So we will focus on that. The Linux address space. Much of like other modern operating systems, and also like VAX or VMS, Linux virtual address space consists of a user portion where user program code, stack, heap, and other parts reside, and a kernel portion where kernel code, stack, heap, and other parts resides. So here's an example of the Linux address space. Like other systems, upon a context switch, the user portion of the currently running address space changes. So if you context switch, the user portion, just like the INVAX or VMS, are currently running address spaces change. The kernel portion is the same across processes, so it's only the user address space change upon context switch, just like in VAX or VMS. So these are one of the characteristics it got or it learned from the past. Like those other systems, a program running in user mode cannot access virtual pages. Only by trapping into the kernel and transitioning into privilege mode can such memory can be accessed. So these are one of the persistent concepts is that we have a user in kernel mode. It's the same with CPU, but in Linux kernel, live Linux x86, we actually implement that. In classic 32-bit Linux, like Linux with 32-bit virtual address space, the split between user and kernel portions of the address space takes place at address 0x C 1, 2, 3, I don't know how many 0 is that, 70 I think, or 3/4 of the way through the address space. But basically it starts with this. So this is where the split between the kernel and the user address space, or 3/4 of the way through the address space. So 3/4 of that, so these are just like 1/4 where you start the divide from kernel to user address. Thus, virtual address 0 through 0x BFFFF, I think it's 7, are user virtual addresses. For the remaining virtual addresses 0x00 through 0xFFF, sorry, 0xFFF instead of 0xBFFF are in the kernel's virtual address space. 64-bit Linux has similar split, but a slightly different points. So again, we're still discussing a 32-bit but so the 64-bit has similar split but slightly different points. But again, in VAX and VMS, we discuss a 32 bits as well. One slightly interesting aspect of Linux is that it contains two types of kernel virtual addresses. The first are known as kernel logical addresses. This is what you would consider the normal virtual address space of the kernel. To get more memory of this type, kernel code merely needs to call kmalloc. So the difference of this with VAX and VMS is because it actually contains two types of kernel virtual address instead of just one. The first is known as the kernel logical address. So to get more memory of this kernel virtual memory, a kernel code merely needs to call kmalloc, kind of like malloc for user, but since it's for kernel, it's kmalloc. Most kernel data structures live here, such as page tables per process kernel stocks, and so forth. Unlike most other memory in the system, kernel logical memory cannot be swapped to disk. So unlike most of the memory such as the user and other kernel virtual memory, this first kernel virtual address cannot be swapped to disk. So this is the another characteristic. Also, again, the data structure, most of this data structure, page table per process kernel stock. The per process kernel we discussed in the initial video of this virtualization to memory has been applied here. So remember that we have this per process kernel stock whenever we have allocate a memory to a process. So this is where it resides, as well as the page table. So the page table we discuss in virtual memory of VAX or VMS that has the copy of a page table of process that then converts it to a physical memory and a page table entry that also allow the easy copy of disk from disk to memory is this. In Linux virtual memory, it's actually in the its logical virtual address. The most interesting aspect of kernel logical address is their connection to physical memory. Specifically, there is a direct mapping between kernel logical address and the first portion of physical memory. So another characteristics or properties is that it has direct mapping to the physical memory. So it's the same with VAX or VMS in which that it has a virtual address for the actual OS code in physical memory, so it's separate. But in this first type of its kernel logical address, it actually has the direct mapping, kind of like the direct mapping on physical memory compared to the next part that we will discuss later, or then second virtual address. Thus, the kernel logical address 0xC and 70 translate to physical address 0x80, 0xC 40 FFF2 0x50 FFFF and so forth. This direct mapping has two implications. The first is that it is simple to translate back and forth between kernel logical address and physical addresses. As a result, these addresses are often treated as if they are indeed physical. So because of this direct mapping, this implication means that it's simple to translate. You don't have this complex translation. don't need to OS to intervene, therefore less time and complexity and faster. So a lot of developer treat this as actually the real physical address. The second is that if a chunk of memory is contiguous, so this is another implication, in kernel logical address space, it is also contiguous in physical memory. So unlike in VOX or VMS, if it's contiguous in virtual address, does not mean it is contiguous in physical address, because that's not how it works. It's a virtualized address. But here in the first type of kernel virtual address, it's actually contiguous in physical memory. So this makes memory allocated in this part of the kernel's address space suitable for operations which need contiguous physical memory to work correctly, such as I/O transfers to and from device via direct memory access. So the I/O transfer to and from device, kind of like in a external USB to laptop to hard disk, this is the memory it uses. These are the memory portion it uses for faster transfer. So these are difference for from the VAX or VMS memory system. That's why it's easy to transfer data now from USB to disk because of this innovation of Linux virtual memory. The other type of kernel address is kernel virtual address. Again, logical and virtual address. So this is actually the non-contiguous part. To get memory of this type, kernel code calls a different allocator, vmalloc, because like virtual malloc. So again, the user is malloc, the kernel actual or physical address or logical address is kmalloc. Here we have vmalloc, which returns a pointer to a virtually contiguous region of the desired size. So this is what you would expect as like a virtual address that C returns, because now we're working on a illusion because the OS is virtualizing memory to serve again large pages to solve the segmentation problem of not allowing contiguous spaces to request a large space in memory. Now, unlike kernel logical memory, kernel virtual memory is usually not contiguous. Each kernel virtual page may map to non-contiguous physical pages and is thus not suitable for DMA. However, such memory is easier to allocate as a result and thus used for large buffers, where finding a contiguous large chunk of physical memory would be challenging. So it's not used in contiguous like that DMA transfer from USB to disk, but it is used to allocate for large, let's say, program. In a 32-bit Linux, one other reason for the existence of kernel virtual address, or the innovation of this, or the combination of OS and hardware policy and mechanism for this, is that they enable the kernel to address more than roughly 1 gig of memory. So it allows the kernel to address that 1 gig of memory despite this small page size. Years ago, machines that had much less memory than this and enabling access to more than 1 gig was an issue, because again we have that segmentation problem where a non-contiguous memory end up being fragmented externally. However, technology progressed and soon there was a need to enable the kernel to use large amounts of memory. So this innovation kind of like in the some programmer of course enable this, contribute to this open source Linux that allows for this adoption of large or allocation of large memory. Kernel virtual addresses and their disconnection from a strict one-to-one mapping to physical memory makes this possible. However, with the move to 64-bit Linux, the need is less urgent because the kernel is not confined to only the 1 gig, the last 1 gig of the virtual address space. So with the 64-bit, the story is different because the kernel is not confined to this portion of virtual address, because again the logical portion is for the the page table, the per process talk. So it's kind of like the small address, also for DMA. But for this virtual address space, since it's only 32-bit, it's crucial to serve this 1 gig. But for 64-bit, it doesn't have that much need because it's a larger space to begin with. So here's the example of this. It's actually used multi-page table, kind of like we have discussed earlier. As you can see, these are the page table where the logical address of this resides in the kernel logical address. So these are the multi-level page table it used for that. So these are the code for multi-level page table control flow. So again, it accesses the TLB, and then it raised protection page directory. So it used page directory first before accessing the PTE address. So here's an example of page table entry in Linux. So it's an x86 page table entry. So this page table entry, of course, it is located in kernel logical address, where it maps to the actual contiguous in memory, but it also has these different capabilities. Yeah, so this page table in that has this different page table entry for each pages allocated in this contiguous memory. So an example of old architecture that has hardware managed TLBs is the Intel x86 architecture. So it actually uses a hardware managed TLB, to be able to support this OS or policy innovation of logical and virtual address, which uses a fixed multi-level page table. The major problem with this approach, however, is that big pages leads to waste within each page, a problem known as internal fragmentation, as the waste is internal to the unit of allocation. So there's a weakness on this, in which since it's flexible, we can assign lower or high pages. It can lead to internal fragmentation, just like we have solved through segmentation. I think it's a problem of base or bound register. Application thus end up allocating pages but only using little bits and pieces of each, and memory quickly fills up with these overly large pages. Thus, most system uses a relatively small page size, in the common case 4 kilobyte as in x86. So most of the pages in x86 or in this Linux virtual memory is actually 4 kilobytes. It only allows that per request, or 8 kilobytes as in Spark v9. Our problem will not be solved so simply, alas. The basic idea behind a multi-level page table is simple. First, chop up the page table into page size units. Then, if an entire page of page table entries is invalid, don't allocate that page of the page table at all. So this is how we do that. That's why it saves us a lot using this multi-page table entry, because we don't allocate if it's not if it's invalid. So the only time we allocate it if it's a valid in page directory. So we managed to make the page table in one size of the 4 kilobytes. So to track whether a page of the page table is valid, and if valid, where it is in memory, use a new structure called the page directory. So the page directory does either be used to tell you where a page of the page table is. So this page directory, it used the page directory to find that. So it has this multi-level translation, right, to actually find that in the physical or the logical virtual address and the virtual address of the actual page. But it check that first if it's valid, or that the entire page of the page table contains no valid pages. Page table structure, because we are focused on Linux for x86, our discussion will center on the type of page table structure provided by x86, as it determines what Linux can and cannot do. So because we're focusing on x86 process, we need to focus on the characteristics of its page table structure, because that hardware will determine what it can and can't do. As mentioned before, x86 provide a hardware managed multi-level page table structure with one page table per process. So again, it has one page table per process. So once you allocate a table or a memory to that, a virtual memory for that process, whether it's a logical or virtual address, it has one page table for it. The OS simply set up mapping in its memory, points to a privileged register at the start of the page directory. So it points to the register at the start of the page directory. So instead of that base register of the actual page table, just like in VAX or VMS, which is the basic, now we're pointing to the page directory, because this multi-level page table is the innovation of the modern architecture. Then the hardware handles the rest, because again, it's a hardware managed TLBs. So the OS gets involved as expected at process creation, deletion, and upon context switches. So the hardware handles the TLB, but the OS only gets involved as expected as in process creation, kind of like in execvp, in deletion, upon context switches of the process. So this is where the trap into the OS TLB goes back. So we added the TLB in this multi-level page table details on the live virtual memory, making sure in each case that the correct page table is being used by the hardware MMU to perform translations. So the OS job is just to make sure that that hardware managed TLB is being used properly. So remember, we only access that if the page directory is valid. Otherwise, we don't need to go through that translation, which makes it efficient. Probably the biggest change in recent years is the move from 32-bit x86 to 64-bit x86, as briefly mentioned above. As seen in the VAX or VMS system, 32-bit address spaces have been around for a long time, and as technology changed, they were finally starting to become a real limit for programs. Virtual memory makes it easy to program systems, but with modern systems containing many gig of memory, 32 bits were no longer referred to each of them. So that's the difference now. So moving to a 64-bit address affect page table structure in x86 expected manner. Because x86 uses a multi-level page table, current 64-bit systems uses a 4-level table. Again, moving a 64-bit address affects the page page table structure in x86 in the expected manner, because again, the mapping or where it starts, instead of 0x800 has some different points, but it's the same structure. Because x86 uses a multi-level page table, current 64-bit system uses a 4-level table. The full 64-bit nature of the virtual address space is not yet in use, as you can see here. So you have unused. So in the 32-bit, we have a different structure. In this, I think we have only 3. Now we have 4 and some unused here. However, rather only the bottom 48 bits. So these are the 32 bits before PD index. So we have 2 before, and page table, the actual page table index and the offset. As you can see in the picture, the top 16 bits of virtual addresses are unused and thus play no role in translation. The bottom 12 bits, due to the 4 kilobytes page size, are used as the offset. So since x86, whether it's 32-bit or 64-bit, has this 4 kilobytes page size, makes that last part an offset, or the bottom 12 bits. So here, in 32 bits, we only have 8 bits. For 64 bits, we have 12 bits offset. And hence, just used directly and not translated. So it just used directly again as a location-based determinality. I don't know if there's that word. So this is where you will base again. You will add the offset to this entire translation, VPN translation, leaving the middle 36 bits of virtual address to take part in the translation. So since we may minus 12 from that 48, we only have 36 bits to perform the translation. But again, it has this page directory, which makes it efficient, because then we only have that page table in the exact 4 kilobits page size, and as well we have that invalid, therefore avoiding access to unneeded pages. The P1 portion of the address is used to index into the topmost page directory. So again, topmost, and the translation proceeds from there, one level at a time, until the actual page of the page table is indexed by P4. So let's say we get into that P4 translation and it's valid, the desired, yielding the desired page table entry. So again, the end goal is the page table entry, kind of like in VAX. So we got that idea from the earlier virtual machines as well. As system memory grows even larger, more parts of this voluminous address space will become enabled, such as this unused space, leading to 5-level and eventually 6-level page table tree structures. Imagine that a simple page table lookup requiring a 6th level of translation just to figure out where in memory certain piece of data resides. Large page table. In Intel x86 allow for use of multiple page sizes. So again, that's the structure of it. It has a multiple page size, not just the standard 4 kilobytes page. Sorry, it's not multi-level page table, but multiple size of 4 kilobytes pages. So like what I've said, it mostly uses 4 kilobytes, but it allows for a per request big page sizes. As seen in VAX or VMS, doing so reduces the number of mappings that are needed in the page table. The larger the page tables, the fewer the mappings. So because this mapping needs translation, so of course the larger your page table, or sorry, your page sizes, the lower the translation. However, fewer page table entries is not the driving force behind huge pages. So the lower PTE, mapping at the end, which is the VAX and VMS ended up to when translating, is not the motivation. Rather, it's better TLB behavior and related performance gains. So, just like in a database, right? A large page size leads to better TLB behavior. So when a process actively uses a large amount of memory, it quickly fills up the TLB with translations. If those translations are for 4 kilobyte pages, only a small amount of total memory can be accessed without inducing TLB misses. The result for modern big memory workload running on machines with many gigabytes of memory is a noticeable performance cost. Recent research shows that some applications spend 10% of their cycles servicing TLB misses. So 10% of the cores or CPU are serve the TLB misses. Huge page allows a process to access a large tract of memory without TLB misses, because you don't need like because you just like have like large pages by using fewer slots in the TLB, and thus is the main advantage. So if you stick with small pages like 4 kilobytes and your workload touches many gig of memory, so let's say we stick with the small pages, you'll need thousands of page translations because you need to translate per pages. Like those pages need to be translated in physical memory into PTE somewhere. You'll need thousands. So, but the TLB only has say 1024 entries. That's just 1024 times 4 kilobyte equals to 4 millibytes of memory directly covered by the TLB, because again TLB is just small. So if your program is working set is 1 gig, that's way beyond 4 millibyte constant TLB misses, therefore it will run slow, and hence the motivation to support large page table. If instead you use 2 millibytes pages, so 2 megabytes pages instead of 4 kilobytes, so 1024 entries times 2 megabytes equals to 2 gig covered by TLB. So you increase the coverage of TLB. Much more of your program's memory footprint can be accessed without TLB misses. So because of that, a large part of the program or most the program will be accessed without misses, therefore it will not run slow. However, there are other benefits to huge pages. There is a shorter TLB miss path, meaning that when a TLB miss does occur, it is serviced more quickly. So aside from that, when a TLB miss does occur, even though you have that large pages already, it will be serviced more quickly. In addition, allocation can be quite fast. In certain scenario, a small but sometimes important benefit. Allocation is also fast. That's another. One interesting aspect of Linux support for huge pages is how it was done incrementally. At first, Linux developer knew such support was only important for a few applications such as large database with stringent performance demand, meaning like airtight reliability. Thus, the decision was made to allow applications to explicitly request memory allocation with large pages, either through the mmap or SHM get call. So to request for these large pages, you use mmap. So this is actually what mmap is used for. Kind of like in a scheduler with NICE, you prioritize it with the Linux CFS scheduler, right? To increase the priority, but in this case to increase the size. In this way, most applications would be unaffected and continue to use only 4 kilobytes pages. So in this way, since you have a flexible, most application can use 4 kilobytes pages, thus that doesn't have stringent performance requirements. A few demanding applications would have to be changed to use these interfaces, but for them it would be worth the pain. More recently, as the need for better TLB behavior is more common among many applications, Linux developers have added transparent huge page support. When this feature is enabled, the operating system automatically looks for opportunities to allocate huge pages, usually 2 MB, but on some systems 1 gig, without requiring application modification. So without your program, like rewriting code mmap for that, this by enabling this in a Linux operating system, it automatically allocate some large pages that your program can take advantage. So that's called transparent huge page support. Huge pages are not without the cost. The biggest, so this is the weakness of this, though, we're just talking this, its edge cases, uses, and its benefits, but this is the weakness. The biggest potential cost is internal fragmentation. So we go back in the internal fragmentation, which we have in the base and bound register. Page that is large but sparsely used. So whenever we have like this flexible, kind of like in a base and bound register, we also have this problem. This form of waste can fill memory with large but little used pages. Swapping, if enabled, also does not work well with huge pages, sometimes greatly amplifying the amount of I/O a system does. Another weakness is that swapping, if enabled, also does not work well with huge pages. So it amplifies the actual I/O of the pages because it's huge. Again, the operating systems works well with the small and clustered pages. So yeah, that's its weakness. So the page cache, to reduce the cost of accessing persistent storage, most systems so because of that, large page has this cost with an I/O, and that it's just too costly to access the disk instead of memory. Most systems use aggressive caching subsystem to keep popular data items in memory. So again, we discussed in a previous video of memory as a cache. Now, we will now further dig deep on this, where we will gonna use this concept to make it actually a cache, to reduce the cost of accessing that storage. So we keep the popular data items in memory, kind of like your Windows application or Windows OS learns your most frequently used programs, therefore kind of like prefetching it or caching it to be able to access it faster. Linux in this regard is no different than traditional operating system. The Linux page cache is unified, keeping pages in memory from 3 primary sources: memory map files, file data and metadata from devices usually accessed by directing read and write calls to the file system. So this file data and metadata from devices are usually accessed by using read and write calls. So these are the metrics it used to organize these primary sources to cache the frequently used pages. Memory map files, we will discuss that later, and heap and stack pages that comprise each processes. So heap and stack, the processes pages, sometimes called anonymous memory, because there's no name file underneath of it, but rather swap space. These entities are kept in a page cache table, allowing for quick lookup when said data is needed. So these 3 entities, the heap and data pages that comprise each processes. So this heap and stack comprise all the processes, and the memory map files and file data and used to read and write are kept in cache hash table to make quicker access. So it's a different data structure are actually being used to access this memory or these pages in memory. The page cache tracks if entries are clean, read but not updated, or dirty, aka modified. So again, It uses the uh, it learned from the past with the VAX or VMS. It used that to track the reference are actively being used, and also it learns from that improvement of replacement or algorithm or clock algorithm. Dirty data is periodically written to the backing store to specific file for data or to swap space for anonymous region. Again, dirty data is periodically written to the backing store to a specific file for a file data or to swap space for anonymous regions. So this specific file data which has file read and write is actually written to a cache, right? To a file data, and the heap and stack pages that comprise each processes is written to anonymous regions by background threads. So there are background threads that from time to time or intervally write this into the cache to make to that data structure, to make that access to those pages a little bit different from a normal access, thus ensuring that modified data eventually is written back to persistent storage. So it also do that so that it periodically written back to persistent storage. The background activity either takes place after a certain time period or if too many pages are considered dirty, both configurable parameters. So one of the feature of this page cache, since it has like quick lookup, it organized that this data, the file data as well as anonymous region, after a certain time or if too many pages are considered data or modified. So it is it's smart enough to track if there's too much dirty pages, and the threads or the background or the daemon thread does the writing periodically, and both are configurable to the developer. In some cases, a system runs low on memory and Linux has to decide which pages to kick out of memory to free up space. To do so, Linux uses modified form of 2Q replacement. So since Linux has this page cache added for quick lookup, it can't just use the improved clock algorithm to implement the replacement fallacy. It needs more than that. So the tailor to how the Linux use the page cache and its table structure. So this here's the 2Q replacement algorithm works. The basic idea is simple. Standard LRU replacement is effective but can be subverted by certain common access patterns. For example, if process repeatedly access a large file, especially one that is nearly the size of memory or larger, LRU will kick every other file out of memory. So it's not ideal, kind of like in the policy in which Linux kick out the big pages, which could be the display, which is not ideal, right? It is not smart or accurate on how things actually access in the real world. So it's still an LRU. It approached the optimal replacement efficiency, but at the same time it handles it edge cases where some large file could remember LRU does not perform well in a loop, or in this case when accessing a large file where you're trying to scan a one-time thing, but since you're using a most recently used and most frequently used kind of thing as an observation with your hardware or as a uh, basis for this algorithm, you end up having been fooled by this type of access pattern, which is we will describe now. So even worse, retaining portion of this file in memory isn't useful, as they are never referenced before getting kicked out of memory. So because LRU retained the most recent file, even though it is not never referenced, it retained portion of this, which is could be used on other pages. Now imagine you're reading a very large file sequentially, say 10 gig file memory, 10 gig file. Your memory is only 2 gig. Each page of the file is read once in order. By the time you finish reading the whole file, the pages at the start will have already been evicted. And here's the key: you never go back to reread them. No temporal locality, but the LRU think it is. If the OS blindly applies LRU, it fills memory with large file you are streaming through. This kick out other useful pages, code, small hat files, the files you're currently using, the code and data structure currently or actively using, metadata that you need repeatedly. Performance tanks because useful pages are evicted in favor of dead file pages. Could be the display, the display process. Modern OS detect this pattern sequential access through a large file and apply special replacement heuristics. So again, it's a modification of the replacement LRU, which is called 2Q replacement. Instead of caching aggressively, they use 2Q replacement. Disregard this, read ahead in Discord. It prefetches the pages in the file cache but mark them as not worth keeping. So it prefetch it into the file cache, the page cache we discussed, but mark them as not worth keeping. So although we're accessing that most common thing, and then we're applying LRU in case that or 2Q replacement in case our memory is full, we mark them as not keeping. So Linux call this file read ahead plus drop behind. Result: useful hat data stays in memory. The large sequential file just streamed through without polluting the cache. So since we have this cache and we're using 2Q replacement policy, it cannot be manipulated by those large one-time file. As LRU equals if something was used recently, it's probably going to be used again soon. This works for loops over an array, repeated function calls, access to configuration files or library, but not in one-time large file. Let's say it's more than your memory. So that's the edge case. So the reason why we also have those anonymous region like heap or stock and the file data and metadata, so read or write, because like these are three things or the hat files are doing, like the access to configuration files or libraries, loops over an array, repeated function calls. So those represents our page cache. That's why we have a different data structure for that. So we have like a cache to access it in one time, like fast cache. We have a different data structure. So say you have memory can hold 4 pages. You're reading a file of 10 pages in order: A, B, C, D, E, F, G, H, I, J. So this is another example why this 2Q replacement is important. Step by step with LRU. You read A in memory, read B, keep A, add B, read C, keep A, B, C, read D, keep A, B, C, D, read E, memory is full, evict A, least recently used, keep B, C, D, read F, evict B, keep C, D, E, F, read G, evict C, keep D, E, F, G, and so on until J. At the end, memory is full of G, H, I, J. Why this breaks LRU's assumption? Page A was recently used at the very beginning, but you never touch it again. Same with B, C, D. Each page is touched exactly once. LRU thinks, oh, You just use page A. I should keep it, but that's wrong. You're just going to move forward. While the OS is wasting memory keeping A, B, C, etc. around briefly, it might evict other actually useful pages like your program, code libraries, or hot data structures. That's why modern OS add heuristics, detect sequential file access, mark those pages as don't keep, drop behind after use. This prevents file scan from polluting memory. Yes, just because a large file page was recently used doesn't mean it will be used again. In sequential access, every page is used once, then discarded forever. This breaks the logic of LRU because when you're accessing a larger than memory. The Linux version of 2Q replacement algorithm solves this problem by keeping two lists. So it keeps two lists, dividing memory between them. When accessed for the first time, a page is placed 1Q called A1 in the original paper. So this is actually how the 2Q replacement works. A page is placed on 1Q called A1 on the first access in the original paper, but the inactive list, it calls inactive list in Linux. When it is referenced, the page is promoted to other queue called AQ in the original, but active in Linux. That's the only time Linux will see that as an active. When replacement needs to take place, the candidate for replacement is taken from the inactive list. Linux also periodically moves pages from the bottom of the active list to the inactive list, keeping the active list to about 2/3 of the total page size. So it creates this two lists. So again, this list, right? We used this list before in a free list, right? This is how we track that. But here we used a magical lookup data structure while at the same time modifying the algorithm slightly a little bit by tracking it using this 2Q. So what is the best data structure for Q? We discussed that in the previous video as well. Linux would ideally manage this list in perfect LRU order, but as discussed in earlier chapters, doing so is costly. Thus, as with many OSs, an approximation of LRU similar to clock replacement is used. So this 2Q approach generally behave quite like a bit like LRU, but notably handles the case where a cyclic large file access occurs by confining the pages of that cyclic access to the inactive list. Because said pages are never referenced before getting kicked out of memory, they do not flash out other useful pages found in the active list. So what is page cache? Let's just briefly discuss this. So what's really a page cache? So we've been defining the 2Q replacement. The page cache is an OS level cache that sits between your process and disk SSD. So when your program calls read on a file descriptor FD, the kernel does not always go to disk immediately. Instead, it first checks the page cache memory to see if the block of the file is already there. If yes, it just returns data from RAM much faster. So this page cache is in RAM. It's just a data structure is already in RAM. So it like collect the write that is or the most commonly used in that part of memory so that you can access it faster. So it sits between your process and disk. If yes, it first checks the page cache memory to see if the block of the file is already there. If yes, it just returns data from RAM much faster. If no, it reads the corresponding block from disk into page cache and then serves it to you. So whenever you are accessing something, again, the replacement policy, therefore, you're likely to access it. Therefore, it puts that into the page cache. And also, it has those criteria said earlier, the heap and stocks of each processes, the file data and metadata, commonly read and write, and the memory map files. If no, it reads the corresponding block from disk into page cache and then serve it to you. So the act of reading a block from disk into memory is literally populating the page cache. That's what the notes mean when they talk about streaming or large file filling memory. So this is also what avoids that large file, using 2Q replacement. It helps the 2Q replacement by not checking it to the disk if it's already in the page cache. So how this relates to file descriptor? A file descriptor is not the page cache itself. The FD is just a handle your process uses to talk to the kernel about a file. The kernel then manages caching of that file's data via the page cache. So FD to system call read or write, kernel page cache, and disk if necessary. So that's the reason why kernel page cache has this read or write or the file and metadata is because of this. So that's why you may have thought file descriptor is page cache, but it's actually FD operations use the page cache transparently. So how this ties into notes you shared. Your notes explain a problem with naive LRU page replacement inside the page cache. If you read a huge file sequentially, say 10 gig on 2 gig RAM machine, every page reads gets pulled into the page cache. LRU assumes recently used will be used again soon. Since we have this page cache, just using LRU will assume recently or most frequently used will be there, therefore not optimizing the page cache. But in sequential scans, this is false. Each page is once and never reused. Result, the big file pushes out hat useful data like code, small config files metadata from the cache. That's why the kernel adds heuristic. Read ahead plus drop behind. Pull the file pages into the cache, but immediately mark them as don't keep. So it had that, don't keep like a dirty pages or access. This way, sequential files don't pollute the page cache with pages that will never be referenced. So we don't just put any data here in page cache, as we can see in the modification of 2Q replacement. We add a dirty and clean list. So in short, yes, reading blocks into memory, filling the page cache is equals to filling the page cache. So once we access it in memory, we fill that in the page cache so that we can access it easily in the future. The page cache is how Linux accelerate both file I/O via FD calls and even anonymous memory via swap. So these are the kind of like a new way or a new implementation of this OS or Linux that makes it differentiate itself to previous VMS. So it used this page cache to make access for most useful pages. So the notes describe how sequential access breaks temporal locality assumptions of LRU and why Linux needs smarter heuristic like 2Q replacement.